They were the largest stars that ever existed. Bigger than anything burning in the universe today. Bigger than anything that will ever form again. And inside each one, buried beneath millions of solar masses of superheated gas, something that should not have been there at all. A black hole, alive, growing, consuming the star from within. Quasi-stars, sometimes called black hole stars, represent a category of objects so extreme that they strain the language of astrophysics. They were only possible during a narrow window of time in the early universe. And if they existed, they resolve one of the deepest unsolved problems in modern cosmology. To understand the scale of what we're talking about, the most massive stars observable today carry roughly 200 to 300 times the mass of our Sun. A quasi-star held up to several million solar masses. The difference is not one of degree. It is a difference in kind. Under that mass, far below the surface, sat a black hole, not ancient, not inherited, but born inside the star itself. Growing, feeding, and in doing so, keeping the entire structure alive. To understand how this is possible, start with how stars form. Stars are born inside vast molecular clouds, reservoirs of hydrogen gas spanning light years, containing thousands or millions of solar masses of material. Gravity pulls the densest regions inward. As those regions collapse, they heat. Pressure builds. Eventually, temperatures at the core reach the threshold for nuclear fusion. Hydrogen nuclei begin merging, and a star ignites. But fusion also ends the star's growth. The energy released pushes outward with enough force to disperse the surrounding cloud. The star is cut off from its source. From that point forward, it lives on what it already has. A closed system, balanced between the inward pull of gravity and the outward pressure of radiation. That balance defines every star we have ever observed. Quasi-stars broke that balance before it could be established. Several 100 million years after the Big Bang, the universe was a fundamentally different environment. Matter was more concentrated. Temperatures were higher, and dark matter, the invisible gravitational scaffold of large-scale structure, had already assembled into enormous formations called dark matter halos. These halos pulled hydrogen gas inward in quantities that have no parallel in the modern universe. The result was clouds of pure hydrogen with masses exceeding 100 million suns, larger than some small galaxies today. In this environment, the ordinary rules of star formation failed. When the first massive stars ignited inside these clouds, their radiation was simply not enough. The cloud was too massive, too deep, too gravitationally bound. Rather than being dispersed, gas continued falling inward, piling onto the newborn star, forcing it to grow far beyond any mass that physics normally permits. Millions of solar masses compressed into a single object. Under that pressure, the core had no stable solution. It collapsed. A black hole formed at the center of a star that was still very much alive. In any other circumstance, that would mark the end. A collapsing stellar core produces an explosion, a supernova, that destroys the outer layers and leaves behind only the black hole. But a quasi-star was too massive. The explosion tore through the interior, but couldn't reach the surface. The star absorbed it. And now it had a black hole for a core. What happened next is unlike anything else in known astrophysics. Normally, black holes are constrained in how fast they can grow. Matter falling toward a black hole forms an accretion disk, a swirling structure of gas orbiting at near-light speeds, heated by friction to temperatures of millions of degrees. That heat generates intense radiation, which pushes back against infalling material. The result is a natural speed limit on consumption. Even surrounded by unlimited fuel, a black hole in open space can only feed so fast. Inside a quasi-star, this limit was overridden. The weight of millions of solar masses pressing down from above overwhelmed the radiation pressure of the accretion disk. Matter was forced directly into the black hole at rates that would be impossible in any other environment. The black hole grew rapidly, continuously, from stellar mass to thousands of solar masses over the course of just a few million years. But the energy released in this process was extraordinary. The accretion disk at the quasi-star's core became hotter and more luminous than any stellar core in history, producing enough outward pressure to hold back the weight of millions of suns. An equilibrium of almost impossible violence. Gravity on one side. The fury of a force-fed black hole on the other. As the black hole grew larger, it consumed faster. As it consumed faster, it released more energy. The star expanded in response. Outward and outward, until in its final phase, it spanned a volume more than 30 times the diameter of our solar system. The largest single object ever to exist in the universe. Powerful magnetic fields threading the black hole's poles drove jets of plasma outward through the star's body and into surrounding space, turning the quasi-star into a beacon visible across cosmological distances. But this was the beginning of the end. The black hole had grown too large. The energy it released was no longer in equilibrium with a weight above it. The balance, always precarious, finally broke. The quasi-star tore itself apart from the inside. What remained was a black hole, of potentially hundreds of thousands of solar masses expelled into the young universe. This is where the story connects to a problem that has troubled cosmologists for decades. Supermassive black holes, the objects anchoring the centers of large galaxies, are too big. A black hole born from a standard stellar collapse begins at a few tens of solar masses and grows slowly, limited by the same radiation pressure described above. Even across billions of years, the path from stellar remnant to object containing billions of solar masses is difficult to construct. And yet observations confirm that black holes exceeding 800 million solar masses already existed less than 700 million years after the Big Bang. The universe simply did not have enough time to build them by conventional means. Quasi-stars offer a mechanism. If they formed in the early universe and produced black holes of hundreds of thousands of solar masses as remnants, those objects would already be large enough to grow rapidly, merging with other black holes, drawing in gas at high rates, and reaching supermassive scales within the available time. The James Webb Space Telescope is now observing galaxies from the first few 100 million years of cosmic history, an era previously beyond our reach. If quasi-stars existed, traces of them may be visible in the light of those earliest galaxies. Anomalous luminosities, unusual spectral signatures, or the unexpectedly massive black holes they left behind. We may not have to wait long. The early universe produced objects of a scale and violence we are only beginning to comprehend. Quasi-stars were among the most extreme, stars that survived their own deaths, fed black holes from the inside, and ultimately destroyed themselves to see the supermassive black holes that structure the universe we live in today. They were not supposed to exist, but the evidence for them is growing.